Hexadecimal. What is it and why do we use it? Well, before we start talking about that, let's talk a little bit about how things are stored inside the machine. Remember, we've been talking about converting integer values, decimal values, into patterns of ones and zeros in a format we refer to as unsigned binary. That's one way of representing an integer in the computer. Now, a computer represents a lot of things other than just integers. It represents letters, it represents colors of a pixel, it represents emojis, it represents all sorts of things. And by representing those things in the machine, we have to know, or our program has to know, how to interpret them. For example, if you have been programming for any period of time, you know that before you can use a variable, you got to declare it. By declaring it, you're telling your program how we're going to interpret those ones and zeros. For example, Java. Whenever we declare an integer in Java, what it's doing is it's reserving 32 bits to store this integer value. Now it's doing it in something called 2's complement, which is a signed version. It's kind of a slight modification of unsigned binary, but it's still an integer where each one of the bit positions for positive values represents a different power of 2. Now, let's go ahead and come up with a 32-bit value. We'll just have 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0. How about we do 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. And this is going to be a base 2 value. Now, I'll give you all a moment to copy that down. Not really into it? Don't feel like copying it down? It makes sense because human beings with just two patterns of ones and zeros, with just two digits that can be in each one of those bits, gets difficult to copy these things down. For example, I've got a string of 5 zeros there. If you had tried to copy this down or typed it into a machine, you might have interpreted it as just 4 or maybe 6, gotten off with count a little bit. There's also a couple of places here. For example, there's a 0, there's 0, 0, 1, 1, 1, 0, 1, 0. There's a similar 0, 0, 1, 1, 1, 0, 1, 0. Those two are exactly the same. If you're copying along, you may not see that correctly. Now, whenever we do something like a phone number, we use something called delimiters, right? So you may have a phone number that's like 423 555 1212. Now, the 423, the area code, you might put a period or maybe put it in parentheses. The 555, the exchange, and then the extension, you might put a dash or a period between those two. Well, we'd like to do something similar so that human beings can understand these long strings of binary, or at least comprehend them a little bit easier. Now, back in the old days, what we used to do is we used to divide these things into groups of 3 bits. All right. Now you'll notice with 32 bits, and 2 things to notice here. First thing is I started on the right-hand side. I started partitioning this number with its delimiters from the right-hand side. And there's a really important reason to do that. It's because you want the groupings to be full groupings of bits on the least significant bit side, and anything that's a partial set of bits, that should be on the most significant bit side. Because when we convert this to a different base, which we're going to show how to do that easily and quickly, you want to make sure that this position fully represents the number of ones for that particular base. Now, with 3 bits, each one of these bits can represent it can be one of 2 possible values. This can be a 0 or a 1, this can be a 0 or 1, and this can be a 0 or a 1. So that means that for this 3 bits, or for any 3 bits, we have 2 times 2 times 2, or 2 to the 3 possible combinations, right? And so each one of these patterns of 3 bits can take on one of 8 possible combinations, starting at 0, 0, 0, which is 0, right? All the way up to 1, 1, 1. Now, 1, 1, 1 would be, well, this is the 4's position, the 2's position, and the 1's position. 4 plus 2 plus 1, 7. So what we have is the ability with 3 bits to represent a value, an integer value from 0 all the way up to 7, all right? That means that this position really represents the 8 to the 0 position, because if you add 1 to that, you get a 1 in the next digit position. You increment the next highest position, which means that we went from 7, add an 8 to 8, which increments the next highest position. This is base 8. And in base 8, well, this position, well, we've got a 4 and a 1, that's 5. We've got a 4 in this position, no other powers of 2. Then 0, 0, 1, that is a 1 in the 1 position. 0, 0, 0, no powers of 2. 1, 0, 1, we've already figured out that that's 4 plus 1, which is 5. 1, 0, 1, that's also 5. 1, 1, 0, 4 plus 2 is 6. 0, 0, 1, that's 1. 4 plus 1, another 5. 0, 1, 1, that is 2 plus 1, which is 3, and then a 0. So it turns out that what we can do is we can kind of create a more human-readable version of this long binary number by dividing or partitioning the number into groups of 3 bits. Doing so and converting each one of those 3 bits to its corresponding decimal value, we have created an octal number, base 8. And so, instead of saying that long binary number, we could say in octal it's 03516550145, okay? Now, some of you are probably asking, why would I do this whenever I can just convert that to decimal? Well, sometimes we actually use the binary value that where we create the binary value. Take, for example, a color in a web page, an HTML color. An HTML color has the amount of red as a byte, 2 nibbles. Oh, by the way, I forgot to tell you that one a little bit. I'll get to that in a second. 1 byte, 8 bits. And then the amount of green in 1 byte, and then the amount of blue in 1 byte. And by doing this, we can actually, as the programmer, create the values that we want in binary and not have to worry about that long mess of converting it to decimal. Wouldn't it be easier to just go ahead and go straight from binary to a representation that's easy to do in the computer? Now, the reason I start with base 8 is, well, because back in the old days, and when I say back in the old days, I mean, oh, we're probably talking 1960s, 1950s, most computers stored values in groups of 6, 12, 24 bits, 48 bits. Things that were divisible by 3, numbers of bits that were divisible by 3. Well, that made it so that whenever we tried to do a quick conversion from binary to something that was human readable, such as octal, it was pretty straightforward. You just grouped the bits into 3 bits, and you didn't get this weird, this weird leftover bits over in the most significant section. The reason why that's kind of changed now is that most computers now store bits as groups of 8 bits or 2 groups of 4 bits. So one memory location will typically have 8 bits. 8's not divisible by 3. So we thought it would be a really good idea if we could come up with a delimiter that would allow us to take this binary number and convert it quickly to something easily human readable that grouped it in 4 bits instead of 3 bits. So let's group this into 4 bits. And notice now we have 32 bits breaks up evenly. Once again, I always start breaking it up from the right-hand side, from the least significant bit side, breaking it up into groups of 4 bits. Last group of bits, Still 4 bits. All right. Now, how many patterns of 1s and 0s can we have with 4 bits? And by the way, I already slipped. I didn't mean to, but I already slipped. 4 bits equals a nibble. This terminology is very common. 4 bits is a nibble. All right. And you'll hear me using that over and over again throughout this lecture. So I now have 8 nibbles. This 32-bit value has been broken up into 8 nibbles. Now, 1 nibble, 4 bits. How many possible combinations of 1s and 0s can I have? Well, I can have 2 values possible for the first bit, 2 possible values for the second bit, 2 possible values for the third bit, 2 possible values for the fourth bit. 2 times 2 times 2 times 2 gives us 2 to the 4th, or 16. So we have 2 to the 4th equals 16. That means that there are 16 ways that the bits in this 1 nibble, in these 4-bit positions, there are 16 ways for them to be set. Going back to our discussion of octal, if we start with 0, 0, 0, 0, all zeros, that is the lowest one. The highest one is all 1s. 1, 1, 1, 1. Well, let's talk about the bit positions again. This is the 1's place, the 2's place, the 4 place, the 8 place. 8 plus 4 plus 2 plus 1, 15. So we can go from 0 up to 15 for each one of these positions. Another way of looking at this is that this least significant bit position can go from 0, 0, 0, 0 all the way up to 1, 1, 1, 1. 15. So you can increment 0, 1, 2, 3, all the way up to 15. Whenever you get to 15 and you add 1 more, this next highest nibble increments. By incrementing this, we're holding this one is holding the number of 16s we've got. If you increment this 15 times, it'll then go up and increment this guy when you go past that, so that this one contains the number of 16s times 16s. This looks like base 16, and it is. We have another term for it. It's called hexadecimal. And sometimes you will see hexadecimal referred to as just plain hex. All right? So, what are we going to do for the symbols? I mean, it's pretty easy. In fact, let's go ahead and make a table of this guy. So I can make a table where I've got binary on one side and hex on the other side. The representation, the mapping, so to speak. Now, with 16 possible patterns of 1s and 0s, half of them are going to start with 0, and the other half of them are going to start with 1. So let's go ahead and figure this out. Let's write this table starting with that idea. So we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then 1, 2, 3, 4, 5, 6, 7, 8 1s. All right? Now, for the second digit, of the ones that start with 0, half of them, the second digit will be 0, and half of them, the second digit will be 1. The same is true for the ones that start with 1. So now we have 4 zeros, 4 1s. 4 zeros, 4 1s. Third bit. The third bit, we're going to have 2 zeros followed by 2 1s, 2 zeros followed by 2 1s, 2 zeros followed by 2 1s, 2 zeros followed by 2 1s. And then the last column is simply going to be alternating 0, 1, 0, 1 all the way down the column. Now the thing about doing it this way is what it gives us is a sorted list of all the possible patterns of 1s and 0s for a nibble. All right? Now, turns out that if we convert each one of these nibbles to decimal, at least for the first 10 digits, we'll get our hexadecimal equivalent. So 0, 0, 0, 0 is a decimal 0. And then we have 0, 0, 0, 1, that's 1. 0, 0, 1, 0, that has a 1 in the 2's position and nowhere else. And then we have 0, 0, 1, 1, that's 2 plus 1 is 3. 0, 1, 0, 0, that's 4. There's a 1 in the 4 position. Then we have 0, 1, 0, 1, a 1 in the 4 position, a 1 in the 1 position, that's 5. 0, 1, 1, 0, that gives us 6. A 1 in the 4 position and a 1 in the 2's position. And then 0, 1, 1, 1, that's 4 plus 2 plus 1, that's 7. Notice that this is the same as the list of octal values, right? The base 8 values when we only had 3 bits. This first bit was not included. The rest of these, now the most significant bit, the 2 to the 3rd position, or 8, is going to be added in. So what we have is 8, and then we have 8 plus 1 is 9. Now, the rest of the digits, we can't continue to use decimal, because if we continued to use decimal, what would happen is this number, for example, 1010 is 8 plus 2, that'd be 10. Well, that takes up 2 digits, and so if I were to do 10 base 16, would this equal a digit 1, this nibble right here? Would it be the nibble 1 followed by the nibble 0? In other words, would this be 8 bits, or would it represent the 4-bit value 1010? You can't tell. So we have to come up with unique new symbols in order to represent that value, those values, actually all 6 of these. Now, wouldn't it be cool if, I don't know, you know, they didn't ask me, but I thought this would be cool if, I don't know, we use maybe exclamation point, @ symbol, hashtag, $, maybe a picture of Saturn, and maybe a, I don't know, how about a question mark? There you go. That would work, right? Because, tell you why I think this is cool. Whenever you tried to convert something to hexadecimal, it would look like cartoon cuss words. No? Don't buy it? Okay, let's do it what they really do it. Let's do it for real. What do they do for real? Well, for real, what they do is they start using letters. And in fact, this is true for any base that goes beyond base 10. They use the letters. So we go 1010 is equivalent to 10, but it's represented with A. 1011, that is a decimal 11. It is represented with B. 1100, that is a decimal 12. It is represented with C. 1101, that is a D. 1110, that is the 14, that is E. And then all ones, that is F. Now, if you do this table and you don't end in F, one of 2 things has happened. Either if you end in G, one of the things that probably happened was you didn't start off with 0. Maybe you started with 1 and just simply numbered and went 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, G. That would be one possible mistake. If you end in a letter possibly E, D, or C, what that means is you missed one of the patterns of 1s and 0s. So those are probably the 2 most likely errors you will see. Now, let's go back to the task at hand. What we need to do is convert this long binary number into hexadecimal using the mapping we came up with in this table. So 0001. We go down the table, 0001, that is a 1. 1101, we go down the table, 1101, that is a D. 0011, 0011, that is a 3. 1010, we talked about that one, that is the A. 1101, that is a D again. 0000, top row of our table, is a 0. 0110, that is a 6, and 0101, that is a 5. So that binary value right up there is equal to 1D 3A D 065. Now, doing this in the notation on paper that we're using, typically I'll just put a little subscript 16 there to represent that it is a hexadecimal value. But most of our coding uses a special representation. What they do is they put a 0x in front of 1D3AD065 in order to indicate that this is a hexadecimal number, not an integer number, not a variable name. It is a hexadecimal number. All right, so why do we do this? Well, the reason is because as human beings, that is a heck of a lot easier to copy down and remember than that is. Only for the humans. And whenever it comes to entering numbers, like the color of a web page, being able to use hexadecimal values makes it a lot easier on us.